And again, we'll just take our lid here, our standard lid, place it in the pan. You always want to handle these with tweezers. You don't want to touch it with your fingers because then you'll get oil on your fingers on the pan. You want to be careful. Definitely wear gloves. If you wear gloves, it's probably fine.
Basically, you should not use your hands.
Yeah.
So either with gloves.
Same thing with the cell. You don't ever take that lid off in there with your hands.
Yeah.
The cell is very, very sensitive, so it'll pick up any kind of contamination. So if you notice, we're using such small sample sizes. So just think about what it's going to pick up depending on where you put it down to. So just be careful wherever you're placing it. Just make sure that the area is clean.
So let's say if we accidentally touch it, how do we clean it?
You can use isopropyl alcohol to clean it, or just make a new sample. But usually, if you use isopropyl, then just let it evaporate for a while. So we got our pan in here. We got our lid put on there, and just make sure that the lid is seated on there properly. The pan's seated on there properly. Come over to the press. Do that.
So once you hit the press, it's now fully sealed?
Yep. So with these, the standard lid, the lid is just pressure put in there. It's not like an actual seal. With the hermetic ones, it's like cold welded onto there, so the metal actually forms together. This one, it's just the lid's just pushed in there. It's not sealed off from the environment or anything. So usually what I do with my indium, once I create it, is take a Sharpie and just put a dot on there so I know which one's which. It's kind of hard to tell them apart once you get them made. I don't have one on me right now.
I have a Sharpie.
I have one.
Very common practice making those cells. In battery, you don't do the battery research. You make your own coin cell. You do something like this. And also many other standardized.
I don't have a Sharpie, but I can see which one's on there just because of the little bulge at the bottom there, so we'll just use that to tell them apart for now. Like I said, with the now we have the reference pan made, we can just use that same reference over and over again until it really gets mangled up. But a lot of customers will just leave that in the cell.
So what if you change the lid?
If you change to a hermetic pan, then you'd want to create a new reference for that. So you always want to have the same lid type as the sample, so they're always going to be matching. So if you're running with a reference pan that's a standard pan, or regular standard lid, then you want to have the sample as the same standard lid. If it's hermetic, you want to have them both match.
Can you tell them physically or from outside what's the standard pan, what's the hermetic one?
Yeah, I'll show you. When you press them, they look a little different. So I'll make one for you right now.
So it's only when you change the pan, right, you have a new reference, depending on the pan that you're using.
Yeah.
The kind of material.
Yeah, it's typically you can rerun them. So this is the hermetic lid. So if you notice on this one, one side is kind of pushed in. Get one out of here. So you'll see on there, it's raised on one side. It's kind of hard to see, but it kind of dips in the center there. Do you see that? So one side's raised up. You're going to want to not do that.
That one is hermetic.
Yeah, this is hermetic. So you're going to want to take this with the so the divot's going in, so the cup's going like that, and then you're going to put this in the lid, so that is going to like match into the lid kind of like that. It's kind of seats it in there so it doesn't move around. So once you get that on there, you would switch this die out, so you have to take this top piece off, go to this hermetic. So again, hermetic is the blue ones, and you can tell based on this color code. So we'll put the top one in first. The top one's always the smaller one. And you'll know which one's which because it won't go in any other way. So put the top one in, take our pan, put it in here. You want to make sure that it's seated properly in there as well. So this one will go all the way down into that hole. Just put the lid on.
Okay.
Go over here to load it. Make sure everything's straight. Like that. And then basically get stuck to the top. Sometimes this happens. It's stuck. If it does that, you can just pull it off. And then you'll see the differences between the two.
Oh,
That one's sealed on the top lip of that pan. The other one's like pressed all the way down into the pan.
so that one for aqueous and
Yep.
hermetic.
Hermetic,
The same pan,
Wait,
but
the
different
hermetic one
lids.
is aqueous, right?
Same pan,
The
just different
hermetic
lids.
one is aqueous.
Okay.
Okay.
So you'll see on here, T0 pan. That's why there's like two colors for this. So that's saying standard lid and hermetic lid. So now we have our two references for both sample types. So what we can do is go to set up a run. So I'm going to set it up in here, but there's another different way to set it up. I'll show you shortly. But typically when you go to run your actual sample, this is how you would come in here and do it. You'd enter in your sample name,
Indium.
which is indium, and you may want to put other stuff in there, but it's up to you. Our sample weight, so we have about
Yes,
7.
consider.
And our pan type, so we're using the T0 aluminum. There's a bunch of different pan types. The ones that just come in your kit are the T0 aluminum and T0 hermetic and the pinhole. So you can put a pinhole in these hermetics, and you would have to select it from there if you do that.
Right now we use T0 aluminum.
Yep, so we're doing T0 aluminum. We put our operator, that's who you are, so
Okay, that's on my way.
yeah, like, you don't have to put
Yes.
that if you don't want to. Project notes, generally I just
Yeah.
put what indium, what my indium sample is. So maybe we'll put like your lot
Yes.
number on there or something. And then you come down here to file name. So this is what the sample, it's storing it under the C drive in this file path. So if you guys wanted to change your file path, you can go up here to options, and then under application and user, you can change the default file path. So if you want to create your own folder
Yes,
or something, it's probably easier because this file path is kind of hard to find. It's pretty buried in there, so you just click this, go in there and change it.
Okay. So once you set it once, you don't have to change it.
Yep. So if you set it this way, you don't have to change it. So that's why I'm showing you this. If you were to set it here, it only does it one time.
Sure.
So going into the options and doing it like I just showed you is to set it always. But yeah, if you do, when you go in here, you'll notice the file name saving as what just the sample name is. So this template down here is what this file name is creating it based on. If you wanted to add more info, you can add like your serial number, the time, date, all this kind of stuff in there if you wanted to, and just click on it, insert, and it'll put it into the run for you. And you can add spacing in here because for whatever reason it doesn't add spacing. Makes it a little easier to see what this is. Now, if you clear everything out, then it'll just default back to the sample name. So once you get all that done, then you come down here to your actual run setup. So this is where you program the steps that your run's going to take, so the actual procedure. If you notice right here, you'll have tests. So generally you'll probably do it under custom. There is some pre-made ones, but it may or may not be useful to you. So if you look,
What experiments? What tests?
these are just pre-made ones. So you'll see like a ramp. So it'll pre-make the segments and everything for you. If you do it under custom, we can come in here and add our own segments from this list. So like I said, generally you'll probably do it under a custom setup for test. So you come in here, custom, name whatever the procedure is, name it, and then you come in here and select each step you want it to take. So on this list you'll see a cool grate. A cool grate is kind of like a stabilization at that temperature. So if you select cool grate at like 150, it'll go up to 150. It'll heat it up as fast as it can to 150. It won't save any data until it finishes stabilizing at 150. So if you want to start your test at 150, then you can the cold rate from here.
Okay.
This is different from the standby. So standby is what it'll go when it's idle. So when it's idle, it'll want to go back to the standby. So after a run, it'll go back to your standby. Before a run, it'll make you go into standby before you can start it.
So yeah, actually this is the initial processing temperature. I mean, so the standby temperature is just during idle.
Yeah, but if you go in here and you go ramp 10C a
But
minute,
the process, I mean, it's gonna be starting using this
you
temperature.
can use you can put a cold rate at any point in the test.
Depends what you need.
Depending on your test.
But if you were to come in here and just say ramp, so if you go ramp 10C a minute to 50, the test is going to stay, okay, I'm starting at the standby temperature at 40C, ramping 10C a minute up to 50.
What is isothermal?
Isothermal is just a hold, so it'll come in, if you want to hold it at whatever temperature it's currently at, so you come in here, say cold rate 50C, I'm going to hold the 50C for 23 minutes. Or you can do it as a ramp, you can do it at the end of the test. Like if you want to ramp up to 200, say I want to hold that 200 for however long, that's what that's for. These buttons right here to move a segment up and down, this is to clear out. So a lot of these buttons, if you hover over them, they'll tell you what they do.
So,
Some of them are pretty self-explanatory just by looking at them.
so if we just want to know like a typical standard, specific heat for material, right? So do you have any standardized procedures?
For specific heat, I think we do, we have a sapphire for that. I'm not sure, because we have a specific heat run where we use the standard material with a known heat capacity. This is a way to like calibrate the heat capacity with the sapphire. It says at 10C a minute, so you probably just do a ramp at 10 to 20C a minute probably for that, for specific heat capacity.
Okay.
In that case, you just do ramp 10 to 20C.
So what's under your default setting? You said this is a custom. So what are the options under your default?
So some of these are like,
Isothermal, cyclic.
Okay.
so if you look at these, it gives you a tempo. This kind of just makes it easier to program it. But if you look in the segments, it's literally just two steps. So a lot of the times, custom just gives you more freedom to add anything you want because you're kind of limited with isothermal because you can only have these two segments and these start and end times. So that's why it's kind of easier to just use custom because you have more freedom that way. So another thing, once you get like your whole test programmed in here, all your steps, you can come up here and save this whole procedure setup. So when you go save, we'll save with, it'll pull in all this information. You can rename it, find a file path for it, and once you pull it in, pull it up from this other button up here, so this is load and save. So it'll pull up everything that you just created in here. It won't save any of this sample info, it'll just save this procedure stuff. If you did want to save like a whole sequence, you could have a bunch of stuff programmed in here. And then you come up here to this button at the top. So if you hover over it, it says save sequence. So that way it would save all these runs with the sample information. That probably may or may not be good because your sample weight's going to change every time. So if you're going to be saving that sequence, you're going to have to come in and change your sample weight.
Oh, okay. What did you put a sample weight? Oh, okay.
It was about 7 milligrams of indium.
Okay, yeah, that's all.
So to do like an indium verification, you can come down here and do verify cell constant and temperature. And this will program the steps to do indium calibration. So if you look here, the steps in this run are based on whatever this standard is. So if you notice when I change this, it gets rid of that standard. So you come here, verify. These are all the standards that we give. You can get your own and add it to this list. If you wanted to add it, you would just come in here to options and down here to temp standards. And this is where you'd add in whatever standards you guys run. So generally we just do indium at 156.6. Some customers will have a multi-point temperature calibration for a better fit temperature calibration, but generally you can just run with the indium and it's good enough for most uses. But again, these are all the other ones you can use. Some of these you won't be able to hit these ranges depending on what cooler attachment you have. So like this one you'll probably max out at zinc and adamantane, because you can't get up past negative 93. But yeah, once you get that programmed in, this will have all this stuff in here. Another thing down here at the bottom, you have all these other options, so you can have it choose to go back to the standby temperature, or you can select a different range for you if you don't want to go back to that standby. Usually we're going to be having the same, these are going to be the same every run. One other thing you can do, we recommend to have it calibrated for whatever ramp rate you're going to be running the test at. So I've calibrated the indium at 10 degrees a minute ramp rate. So you may find you want to run at a lower or higher ramp rate depending on your sample, based on this. So sample prep. This right here, determining sample size. This will give you like a general guide for how big of a sample to use and what heating rate you're going to want to run. So depending on what you're looking for, you may want to run at a different ramp rate. Like I said, in that case, you're going to want to recalibrate your indium sample.
The general guidelines for any materials,
Yeah, pretty much.
for all the
So we're doing a melting point with indium. We want around 2 to 10 milligrams and our heating rate of 5 to 10 C. So my sample is 7 milligrams and I calibrated. We're going to run it 10 C a minute up to 186. If you guys did want to recalibrate, down here at the bottom we have this calibration tab. So this has all your calibration data, so it tells you when the last time the baseline calibration was done. So the baseline on the DSC is basically when the cell is empty, we want a straight line at 0. So this calibration is just making any corrections to try and get as straight of a line at 0 as possible. With this cell, it's a pretty basic heat flow. So the only corrections we can make are a correction for the slope of the signal and a correction for the offset. So this T1 calibration is the baseline. So the reason it's called T1 is because there's the difference between the two sample and reference platforms is your T1. And there's more, the higher end DSCs will have more refined heat flow, so they have a T4 and a T4P. Those are the higher end ones, so the base heat flow is T1. So if you look at this, I'll show you this real quick. So this is your getting started guide. This is like your manual. I think I showed you guys earlier, but the way you get to this is thermal discovery manuals on the desktop. This is kind of just a quick start guide for everything. If you go down here though to the DSC, this is where it's getting its heat flow signal. So the signal that the DSC is measuring is this Q heat flow. So you'll see your delta T, difference between sample and reference thermocouple. So with this DSC, this is the most basic heat flow. This is where we're getting our heat flow signal. So difference between these sample and reference. But if you were to have the higher end one, this is the more refined heat flow. There's just more terms in it. But this isn't the heat flow you guys have. But if you were to read about this, it would tell you what it is. Again, yours is the basic one, so it's just this delta T. So when we come in to look at our calibration run, we have our T1 baseline calibration run. This is what the run's going to look like. So we have the signal delta T uncorrected. Again, that's the change in the sample and reference. So ideally it'd want to be the same, but manufacturing tolerances and all that's going to create some differences between the two. So when we heat it up, we go full range of the instrument, so negative 90 to 400 for this calibration run of the baseline. And generally you want to see a pretty smooth, consistent line. So the reason we want it to be smooth and consistent is so the calibration can create a correction for slope and offset from 0. So it's just, again, it's just trying to create an empty cell run at 0, because ideally an empty cell DSC should be at 0 for the baseline. So that way you get the true reading of whatever your sample is.
Okay, so this baseline calibration, by reference to empty cell, you mean 1 ampere reference cell and a 1 ampere.
Completely empty, no pans at all.
No pans at all?
Nothing in the cell at all.
Nothing.
Yep. So this test is done, nothing in the cell. So you would come into the software to set this up and come into calibration setup. So you'll see at the top data and setup. Data is just all of the runs that I did, all the current applied calibrations for this. And then under setup, this is where you would actually calibrate the baseline. So you come in here, do T1 baseline. These other tests right here, cell conditioning and baseline conditioning, are just pre-calibration runs. Since your cell is new, you don't really have to do these, but maybe over time your cell gets dirtier, you find you may have to do these. Cell conditioning is mainly for moisture, so what it does is turn off this cooler and it'll hold the cell at an elevated temperature at 75 degrees with the cooler off, and it'll kind of just melt off any of the frost and dry out the cell for you. That's what the cell conditioning run is. So if you select that, you'll see 75C and 120, so it holds at that high temp for 2 hours to dry it out. Like I said, generally with your new cell, as long as it's clean, you won't have to do these. You can just jump right into T1 so long as the cell is clean. I'll get into like how to clean the cell and what to look for as far as contamination of the cell if you suspect it. But for right now, come into T0 for calibration. You'll see these are all the default settings that they give you for this. I'd say just keep the default settings when you go to calibrate this. So all you'd have to do when you come in here is change probably your operator and whatever your project is. Keep all this the same. This will perform a verification run after this. So after calibrating it, it'll do another of the same exact run with those offsets applied just to make sure that the baseline looks good. So keep it all the same. You go in here, Q all. You'll see it said 2 calibrations applied. So we'll see these 2 runs in here. So again, this is the calibration run. This is the verification. If you look here, test T1 heat flow versus verify heat flow.
Okay. And after you've done the calibration, how do you use that data to,
It'll apply it automatically.
Automatically?
Yeah. When you do it, just for reference, it'll come up in here, and it should pull up the screen after you finish. So once it goes back to idle, it'll pull up the screen and saying applied.
Okay.
So you always want to, after you run a calibration, you always want to come into this data tab and make sure that it applied at the time that you ran it.
And how often we have to do this again?
This one really doesn't have to be done too much, so long as your baseline looks good. So maybe periodically you may just want to do a verification of the baseline, just make sure it's good.
Okay.
Like so long as your cell isn't contaminated and your lid isn't all mangled up and you guys take care of your cell, you don't really have to do this so often.
Okay.
Usually it's only done like if you suspect contamination or if your baseline isn't great. Like if you're seeing huge slope in your sample that you suspect is from the baseline, then you would probably run the empty cell baseline just to check to make sure that it is in fact the baseline and not your sample. And then if it is, then you would come in here and recalibrate the baseline. So generally you don't have to do this, but if you suspect, like I said, in those cases, then that's when you probably want to come in and recalibrate it.
When you say cell, are you talking about the entire case? The casing of whatever the sample is going into?
No, so the cell is where the readings are taking place. So when you run this calibration, it's with empty cells, so literally nothing in the cell, no pans, nothing.
Okay.
Nothing on the sensor platforms at all. Yep, so this is the one run. It'll apply this automatically with this calibration results for you.
For each run, we need to use T1 calibration.
No,
We need to
no. This is only just for baseline.
Yes.
So, like I said, once you calibrate this baseline and your cell is clean, you can keep running that. You don't have to rerun this until you suspect that the slope in your sample it may be coming from a bad baseline. So, say you run like an indium melt, for example. Generally, your sample is going to vary depending on what it is, but see how the indium's nice and flat at 0? If your indium's like shifted down here, it's like -1, or if you see like a really big slope in it, it's not straight anymore, then that's probably something with your baseline. So that's when you want to recalibrate it. Generally, indium's a good way to tell if your baseline's good or not. Depending on your sample type, like if you're looking for glass transitions, your baseline performance is more important because glass transitions, the reaction's so small compared to indium, so we're looking at like watts a gram here. Glass transitions are pretty small, so they'd probably be like a quarter of this transaction, or even smaller than that. There's going to be really finite stuff happening with some of your samples, so That's why it's good to have a good baseline performance.
Are you gonna show us how to interpret the data afterwards?
Yeah, I'll show you some basic stuff, like how to analyze it, basic stuff like that.
Yeah. So the processing of the data is also in this software.
Yeah, it's in the same software. It's all combined.
Okay. It used to be a different.
Yeah, on the older DSCs it was a universal analysis, which is a separate software. But this one, it's all combined into one, so it's kind of nice for that, at least. Like I was saying though, once you get that baseline run done and this pulls up, you would come in here, it would verify the baseline, does the exact same run. So I'm going to show you my verification from today. This is what it'll look like. So the scale right now we're looking at is milliwatts. So this is very fine scale. And again, ideally we want it at 0 and as straight as possible, but because of manufacturing tolerances, obviously it's not going to be perfectly 0. But generally, I think the spec for this is 50 microwatts of drift and 50 microwatts of bow. So this one is pretty good. The drift we take the drift from like -50 to 300. So the drift we're seeing on this is about 7 microwatts. And like I said, the spec is about 50. And then the bow, so the bow is just how much it curves. So we're taking the point, how much that point curves. The drift is just signal change, so -50 at this point, how much is it changing at 300? Kind of a way to tell it.
Why you don't use the whole range?
Because there's a startup hook that is associated with the cooler. So once the run starts, it takes a little bit of time for the heat flow to stabilize at the start of the test. And once you start heating it up too, the baseline starts to get a little more non-linear, I guess you could say. And you always want like a pretty linear baseline, that way it's better to correct it. And this is my calibration run, so when you run your calibration run, you don't want to see any kind of spikes or anything in that indicates contamination. So this would be an ideal baseline. If you were to see spikes, again, that's something contaminated. If you see a spike at 0 or 100, typically water, then you would do that dry out that I mentioned, the cell conditioning, which is the heating at 75 C for 2 hours.
Sometimes the sample will come out to be
humidity or some contamination.
if you put too much, experience.
Yes.
So this baseline right now is 7 microwatts of drift and 9 microwatts of bow. So that's well within the specs that this should be in. So when you run it, you expect to see it around there. If you get like 100 microwatts, then I would definitely try and recalibrate. It's all depending on your sample too. Like if your sample has big transitions like indium, a lot of that baseline fluctuation will kind of get hidden out because it's such a big transition. So you just got to think about the scale we're looking at right here is in little milliwatts. And the indium one that we did is in watts, so really small scale. But again, yeah, DSC ideal baseline right here. And this will change depending on every time. Like, once you start running it, this is going to change slightly. And the biggest thing for the baseline is making sure that that lid surface that I showed you earlier in the cell is clean and that there's not nicks all over that.
Okay. Can you show us how to put it in? Can you show us how to put it in?
Yep. Yeah, so I'm going to pull up in the help section. If you go up in here and we search for the keyword cleaning. Cleaning Discovery DSC. So cleaning a DSC cell is a baseline anomalies are often the side of a contaminated cell, and a baseline anomaly is either like a spike or any kind of other weird things you see in the cell that aren't something you would expect your sample to do. So the way you would clean this, obviously first take out your pans, and then you would come down here. So burning off contamination is the first step that they recommend. So you come down here to burning off DSC with RCS. So the RCS is what we have here. If you notice at the bottom here, refrigerated cooling system, RCS.
Okay.
So depending on what type of cooler you have, it's going to change the cleaning steps you're going to take. So if you read this, it says begin cleaning by heating the cell with an air purge to 50 C above the highest operating temperature. So if you do have in the future an air purge line set up, you can have it in the software to switch to that air purge and then heat it up to 400C. If you don't have that air purge, what you can do is do the same thing, heat it up to 400C. And once it gets up to 400C, you would just take the lid off and then pull this lid off as well.
What do you mean air purge? Like you use compressed air? Or?
Yep. So you, like I was talking about earlier, how you may want to expose your sample to oxygen or something.
Okay.
You would put that on the line, the gas port 2 on the back of the instrument. And you would, during the test, you would switch to that air. That's if you do have that air purge. If you don't put that air purge, this is another way to just burn off anything.
Okay.
So you heat it up to 400C. Just come over here, open the lid, and just do it like this for like 30 seconds just to give it time to burn everything off at that high temperature. And then you just put this lid back on, and put this back on. And just be very careful when you're doing this. You don't want to burn yourself. Always use the tweezers.
I see again.
So you're just taking this lid off and you're just oxidizing. You're just exposing it to the air to burn off everything, basically.
Yeah.
And the test setup that you would do for this to burn it off. You come down here to procedure setup, and you want to do it under cold rate. So you're doing a cold rate. You can run up to 450. I recommend just doing it at 400. So you're doing a cold rate at 400. Yep.
For majority of naturals, the others.
This is for just cleaning off the contamination. This is just burning off the cell.
Exactly.
So any kind of contamination, you're going to want to burn it off at 400.
Contamination is 400.
This is not for
It's not
this
for,
is just for burning off
it's
contamination.
for cleaning just.
So you do this test, start it up, the cell will heat up to 400C. Once it gets up to 400C, you can stop the test and then open the lid. So what I usually do, let it get up to 400C, stop the test, and then right after I stop it, I open the lid up and do how I just showed you. Take that lid off, let it burn off for about 30 seconds, and replace the lids on it, and then let it cool back down to room temperature. And then after you do that, you may want to run another empty cell scan, so no pans in the cell. Run another scan, see how the signals look. If you still see contamination, you may need to go into the other steps that the details in this online help. So generally, a lot of the times you can get away with just doing the burnout, but if it does, you'll see the steps in here. So it's saying, after cool down, lightly brush out the cell with a small fiberglass brush. So this fiberglass brush is the brush that they're talking about. So this brush you would use on those sensors on the cell. So you would come over here. You have to be very careful with this when you're cleaning this out. You would just go over top of these two sensors, kind of like a pencil eraser, just kind of back and forth, brushing everything off of it. Don't ever go into this center thermocouple. So down here in the center, I never touch that, because if you break that center thermocouple, you'll blow out your cell completely and you'll be out like $10,000.
So these are thermocouples.
Yeah.
So can you repeat again? What did you clean it?
We're just cleaning these two sensor platforms off. You can clean around the sensor platforms in this silver area right here. To clean it off, you can clean off this gently. Just be careful when you clean this off. Don't want to hit this center thermocouple. That's called the T0 thermocouple.
These are
if you hit that thermocouple and break it in the center, then you're below your cell.
Where is located? Where the thermocouple?
Exactly the point.
You see the center thermocouple in the center right there? Very center.
Oh, like in the center.
Very center. Don't ever touch that with this brush. Always just use it on these two top sensors. So the two platforms, you would just brush these lightly with this brush. And then after you're done brushing them, you would want to get a can of compressed air, like computer dust or something. Just do a couple quick squirts just to blow out any of the fiberglass splinters from this. When you use this brush, it's going to have dust and fiberglass splinters that come off of it. So you always want to blow off.
Where is thermocouple? Exactly.
These are two thermocouples, so this is reference and sample.
Yes.
And the center is in the very center. So if you look closely, you can see it's like two little dots. That's the T0 thermocouple. So there's 3 thermocouples in total.
3 thermocouples.
But I only recommend hitting the sensor or the sample and reference, the 2 platforms. And like I said, you can also clean around them. You just have to be very careful when you're cleaning around them to not hit that center one. And when you're cleaning this out like that, you're kind of just brushing it out. you just want to be careful not to nick this edge at the top here. So just don't nick this edge because this metal piece can kind of mar this edge. So you just got to be careful when you're doing that.
And never put this side down.
Oh, I always put this lid with the upside up, so that way you don't mess up this edge of the lid. Because again, that's for best baseline performance. You don't want this all messed up because it'll affect it. Just put this back in here. And just kind of just try and get it as centered as possible.
So how do you put that into the?
You put what?
How do you put that?
Samples? Just place it right on top of these sensors.
Just like that?
So again, the sample is the one that's closest to you.
Yeah, either of the tops. Either of the tops. You can put on either of the tops, yes?
No.
No, you want to put it closer.
Always put your sample on the back. Reference is always on the back. Sample you want to keep close to your heart, so sample is closest to you. Reference is in the back, always. So a lot of the times customers will just leave their reference pan on there and just take off the sample.
Okay.
So say we're running
That
a
one is
test.
sample, the other one is reference.
So the closest one is sample. Furthest one is reference. So like I said, sometimes customers will just leave the reference pan on there. So once you're done a test, they'll just take this off, discard that, and leave the reference on there. Come back with a new sample, put the new sample on there, and start the other test. So you can rerun that reference pan. When you put these on here, you kind of just make sure that they're as centered as possible. On this
What is
sensors.
reference right now? What is reference?
It's nothing.
It's nothing.
Always nothing. Just empty pan always.
Just empty fan and lid.
Yep, always.
Because if you take out the pan, what kind of energy itself?
Yes.
Never anything in the reference pan. Everything that you're going to be testing is in your sample pan. So always empty reference pan.
The difference will be the actual
The difference for the so one you have your sample, the other one is empty.
the container.
Just
Because you put the sample in your container, the same container.
Yeah.
Kind of like how you have a balance.
Exactly.
Yeah.
I got it. What is the philosophy?
Makes sense.
Yeah. So if you read through this, it'll mention how to do this with the fiberglass brush. What I just said, removing the debris with the compressed air, and it's saying run a baseline. If there's an improvement, repeat the procedure. You can also hold longer at the higher temperature, but generally I don't really hold that long. I do it, the max I would hold at 400C is maybe a few minutes. I wouldn't hold at 400C for too
So
long.
let me ask you this one: the lead and pan-off, sample and reference should be the same.
So can you repeat that, sorry?
The lead and pan-off, sample and reference should be the same.
Yes, always.
Also, if you're changing the type of sample that you have, or changing the pan or the container, you have to change the reference on that.
Correct.
Yes.
So
Okay.
that's why.
That makes sense.
Yeah. So you always want to have the same matching type.
Should be exactly the same.
Okay.
The only difference is that one has a sample.
Exactly.
Okay.
Some other methods to do it. You can use solvent. So what I do sometimes is dip Q-tip in isopropyl alcohol and kind of get like a Kim wipe and just dab off the excess solvent. And then you can use that on those sensors as well, like I showed you with the brush. You can use that Q-tip to clean out anything in the cell as well. Generally what I do is I start with the solvent and then do a burnout, so that way it'll burn off all the solvent, and then hit it with that brush and then blow out that brush and then run a baseline test and see how it is. Usually that's good enough to clean off most contamination. Again, this will tell you all this stuff, so when you forget everything that I told you today, you can just search cleaning, and come in here and find it. Also, we have a video on our YouTube channel that details how to do the cell cleaning, so when I send you all the documents for this, I'll send you that cell cleaning on our YouTube. But if you look up, I think if you just look up DSC cell cleaning on YouTube, I think our video will show up. Our YouTube channel is TA Tech Tips, so you should see like our logos and everything on there, so you should be able to find it pretty easily on YouTube.
Let me ask you this. So this software, how many computers can we use?
You can have it on any computer. If you go to our website, you can download it straight from there. That way, students, they can have it on their home PC.
Data analysis?
Yep. Yeah, so